Every time you pull into a gas station, you're pumping a clear, fast-burning liquid into your tank. But if you saw that liquid starting point, you wouldn't believe it came from the same substance. Crude oil, straight out of the ground, looks like thick black tar. It barely pours. It smells like asphalt. And yet, somehow, within a few weeks, that same black sludge becomes the exact fuel that lets your car ignite a spark and go from 0 to 60 in seconds. By the end of this, you'll understand exactly why a substance that looks like roofing material can become one of the most precisely engineered products on the planet. And once you see the process, you'll never look at a gas pump the same way again. Because what's actually happening between the oil field and your fuel tank isn't a quick filtering job. It's one of the most tightly controlled industrial transformations on Earth, running around the clock, at massive scale, just to keep your car running. Let's start with what crude oil actually is, because most people picture it as one single thing. It isn't. Crude oil is a mixture, a messy, tangled combination of thousands of different hydrocarbon molecules, all mixed together in a single black liquid. Think of it like a junk drawer. Not a toolbox where everything is sorted and labeled. A junk drawer where rubber bands, batteries, screws, and old receipts are all thrown in together with no order at all. That's crude oil. Inside it are short, light molecules that want to become gas at room temperature, and long, heavy molecules that stay thick and sludgy no matter what. They're all coupled together in the same shipment, and none of them are usable in that form. To understand why, you need to understand hydrocarbon chains. Every molecule in crude oil is built from carbon and hydrogen atoms linked together, and the length of that chain determines what the molecule becomes. Picture a freight train. Short trains, just a few cars, are light, they move fast, and they naturally want to float away as gas. Long trains, dozens of cars coupled together, are heavy, slow, and they sink into a thick tar like sludge. In crude oil, you have short 4-car trains and 100-car trains, all linked into one shipment, all rolling down the same track together. Nobody sorted them. That's the raw material a refinery has to work with. And that's exactly why crude oil straight from the well is essentially useless. You can't put it in a car. You can't burn it cleanly. Pour it into an engine, as is, and you likely destroy that engine within minutes, not power it. Before crude oil becomes anything useful, it has to be pulled apart, piece by piece, chain length by chain length. Here's where it gets counterintuitive. By common sense, separating thousands of different molecules that are physically tangled together should require some kind of complex chemical process, something that breaks each molecule apart individually and sorts it by type. But that's not what happens. Refineries don't chemically dismantle crude oil to sort it. They just heat it. That's the whole first step. Heat it up, and the oil sorts itself. Here's why that works. Every hydrocarbon chain has an exact boiling point, and that boiling point depends entirely on the length of the chain. Short chains boil off first, at low temperatures. Longer chains need much higher temperatures before they'll turn to vapor. So when you heat crude oil in a furnace to around 700 degrees Fahrenheit, the mixture doesn't stay a mixture. It splits itself apart, layer by layer, purely based on temperature. Think about boiling a pot of mixed liquids on your stove. If you had a pot with water, alcohol, and syrup, all mixed together, and you slowly raise the heat, the alcohol would evaporate off first, then the water, and the syrup would stay behind the longest. Nobody stirred it into separate piles. The heat did the sorting. That's essentially what's happening inside a refinery, just at an industrial scale, with thousands of different hydrocarbon chains instead of 3 liquids. Now let's follow that hot vaporized oil into the machine that actually performs the separation, the distillation tower. These structures are massive, sometimes over 150 feet tall, built like narrow steel skyscrapers standing next to the refinery, visible for miles across the flat industrial landscape that surrounds most refining complexes. Heated crude oil, now partly vapor and partly liquid, enters near the bottom of the tower. And inside that tower are dozens of trays, stacked one above another, each one slightly cooler than the tray below it, creating a precise temperature gradient from the scorching bottom all the way up to the relatively mild top. As the hot vapor rises, it passes through tray after tray, and every time it hits a tray that's cooler than a particular molecule's boiling point, that molecule condenses back into a liquid and gets pulled out at that exact level. The heaviest molecules, the ones that need extreme heat to vaporize at all, condense almost immediately and get drawn off near the bottom. These become thick products like asphalt and heavy fuel oil. Slightly lighter molecules make it a little higher before they condense, and those become diesel. Lighter still, and you get kerosene, used for jet fuel. And the lightest molecules of all, the short-chain hydrocarbons that barely want to be liquid in the first place, keep rising all the way to the top of the tower before they finally condense. That's your gasoline. Picture the tower like a 50-story office building with only one working elevator, and everyone getting on that elevator has a different amount of weight strapped to their back. The heaviest passengers can barely make it off the ground floor before they're exhausted and step out. Slightly lighter passengers make it up 10 or 20 floors before they give up. But the lightest passengers, the ones barely carrying anything at all, ride all the way to the top floor before they finally step off. That's exactly how the tower sorts hydrocarbons. Weight determines how high they get before they condense and exit. No human is standing at each tray making that call in real time. Temperature alone decides who gets off and where. So at this point, you'd think this story is basically finished. Heat the oil, let it separate by weight, collect gasoline near the top. Done. But there's a problem, and it's a big one. Straight distillation alone doesn't produce nearly enough gasoline to meet demand. Only a small percentage of crude oil naturally consists of those short, light molecules that become gasoline. The rest is mostly medium and heavy chains. If refineries only used distillation, gas stations across the country would run dry within days, and prices would spike overnight. This is where refineries do something that sounds almost violent. Something you'd never expect from a process built on careful temperature control. They break the heavy molecules apart on purpose. It's called cracking, and it's exactly what it sounds like. Refineries take those long, heavy hydrocarbon chains, the 100-car freight trains, and expose them to extreme heat, around 900 degrees Fahrenheit, combined with high pressure and often a chemical catalyst. That combination physically snaps the long chains into multiple shorter ones. Think of it like taking a long, uncooked stick of spaghetti and snapping it in half, then snapping those halves again until you're left with a handful of short, usable pieces instead of one long, unwieldy one. That's cracking. It takes molecules that were never going to become gasoline naturally and forces them into the exact length that does. Cracking alone can boost the gasoline yield from a barrel of crude oil dramatically, turning what would be a mediocre gasoline output into one where more than half of every barrel becomes usable fuel. Without this step, gasoline would be far more scarce and far more expensive than it is today, and the entire economics of driving would look completely different. Some refineries also run a second process called reforming, which reshapes certain molecules to boost octane even further, squeezing extra performance out of fuel that would otherwise be mediocre at best. Between cracking and reforming, refineries are essentially manufacturing gasoline out of raw material that was never naturally suited to become gasoline in the first place. So by now, the crude oil has been heated, separated by boiling point inside the distillation tower, and had its heavy leftover molecules cracked into lighter, usable ones. But it's still not gasoline yet, not the exact product that goes into your tank. The next step is blending. Refineries mix different hydrocarbon streams together in carefully controlled ratios to hit an exact target for octane rating, the number that determines how resistant the fuel is to knocking inside your engine. Additives are blended in too. Detergents to keep your engine's fuel injectors clean, corrosion inhibitors, and seasonal adjustments. Since gasoline sold in the middle of summer, is actually formulated slightly differently than gasoline sold in the dead of winter to control how easily it evaporates in different temperatures. Get that evaporation rate wrong, and a car can struggle to start on a freezing morning or vapor lock on a brutally hot afternoon in the middle of summer. So every batch is tuned like a precise recipe, adjusted region by region and season by season, long before it ever reaches your tank, using formulas refined over decades of trial and error. From there, the finished gasoline doesn't get trucked straight to your neighborhood. It enters an enormous underground pipeline network, sometimes traveling over 1,000 miles from refinery to regional terminal before ever touching a truck. At the terminal, it's loaded onto tanker trucks for the final short trip to your local station, often arriving within hours of a truck driver picking it up. So think about what actually happened here. A black, tar-like sludge, pulled out of the ground, filled with thousands of tangled, useless hydrocarbon chains, gets heated until it sorts itself by weight, gets its heaviest leftover molecules physically snapped into shorter, usable pieces, gets blended to an exact chemical specification, and gets shipped over 1,000 miles through steel pipelines, all before it reaches the nozzle in your hand. It's essentially an assembly line that takes raw scrap material and turns it into a precision machined product, except the raw material is thick, black sludge, and the finished product is clean enough to ignite with a single spark inside your engine. Not one shortcut in that chain, and not one step that could safely be skipped. And that raises another question. How does that gasoline actually make that journey? 1,000 miles through pipelines, buried underground, crossing entire states, without a single drop ever being touched by human hands. That's a story about pressure, pumping stations, and an invisible network running beneath the highways you drive on every single day, quietly keeping every gas station in the country stocked, without a single visible sign of the machinery underneath your feet. And that's exactly what we're breaking down next.